Hi, everybody. So I'm Miguel Barajas. I work with Kathy Mills at the Gulf of Maine Research Institute. Oh my gosh, my brain. I'm also a grad student at Maine working with Lisa Kerr. And I'm just going to do a little bit deeper dive into the population dynamics component of the Navigating the New Arctic project. Okay, so you guys have seen these slides before, so I don't need to go over it. But there's us right here. Like Damien was saying, all these arrows are kind of like one-way arrows, but you can really think of them as once you get down to this level, is that there's going to be a lot of feedback mechanisms in play here. And so it's going to be a really interesting collaboration on how we kind of connect these parts and how they kind of feed back into each other in the overall greater project. Okay, so here's kind of the conceptual schematic of the population model. There are 3 different bins here that we're kind of using to describe these population processes. There was some back and forth on, how complex do we want to model these? Do we want to go down the stock assessment route and have 5-millimeter bins and these different length bins? Do we want to look at I don't know, there's a lot of different options here. We kind of chose a fisheries perspective where we're really thinking about harvest, and so particularly, are you at harvest size, or are you below or above? And depending on where you are, harvest size can mean many different things. But roughly speaking, for each kind of population model that we'll be representing, they'll be broken down into these bins. And each bin will have kind of stage-based parameters associated with them and different biological processes. So mainly this below harvest size bin is really about like, okay, lobsters have been, in the pelagic stage and they've just settled down to the bottom. Now what happens? So we're thinking about growth mechanisms here. We're thinking about predation, natural mortality. And the way we kind of model this is there's going to be a probability-based parameter where, if you survive, do you stay within this stage or do you move to the next one? We're using this distribution method to kind of estimate stage duration, and this is tied to kind of growth rate trajectories that are being driven by temperature processes. So if temperatures ramp up, growth rates accelerate, the time you'll spend in that stage will kind of be shortened, and you'll move on to the harvest size sooner. And likewise, there's a duration within that size. So, there's a minimum legal size, there's a maximum legal size. And, if you're lucky enough as a lobster, you will grow, survive, and reach the next stage, and, you're safe from the fishery. But, in this harvest size here, we have this additional component of fishing mortality, and then, the above harvest size, that's really a measure of, natural mortality, shell disease, predation, if, certain conditions, but for the most part, if you make it to this size, you're safe. And so all of these mechanisms will be informed through the ocean modeling and the larval lobster modeling. So here I have reproduction feeding into this below harvest size. Now, currently we have these recruitment processes in play in the population model. However, as we integrate the larval lobster modeling, we're going to have a process here where the larval modeling that Andrew's doing will supply sort of spatial patterns and settlement strength that will kind of feed into this beginning stage. Okay. So some of the research questions that we have in the particular mechanisms that we're looking into, these are all based around temperature. So we have growth, we have reproduction, we have recruitment. So here's the growth model that we're working with here. So we're assuming this continuous von Bertalanffy growth model. So recognizing that lobsters molt, they don't actually grow like this, but with this ambitious project, you have to choose, versus simplicity versus complexity. And here we're going with this this method here. So depending on the regime, whether you're in a cold or a warmer regime, you're going to have different growth trajectories, and those are going to impact, the main focus here is how many years does it take for a lobster to settle on the bottom up to that, harvest size. And so we'll be kind of tracking cohorts as, the simulation moves forward, kind of recognizing that there's going to be variability here. And we can also, as we look into growth mechanisms a little bit deeper, compare our results to things that are going on within the stock assessment, looking at alternative growth approaches and seeing, do these trajectories match up with what's out there in the science. And so, folks here, Ruby, looking at size and maturity of crustaceans, we're going to be doing kind of similar functional responses here where, as size increases, there's a probability that you kind of mature to the reproductive stage, and this will also be temperature dependent. And this is where some really interesting interactions occur with the fishery. So, the legal size is, 82 point something, and depending on the temperature regime, you can have individuals that are, maturing, but then being fished out either before they're able to contribute to the population. And so those legal size limits really matter, particularly in this lobster fishery where a lot of individuals that just make it to that size are pulled out. And then also, associated with conservation measures, looking at like V-notching prevalence and how does that affect population dynamics overall. So another set of research questions we're looking at are how does temperature affect mortality? So disease prevalence. So like we were having that conversation earlier about epizootic shell disease. There's a number of folks at Bigelow that are actively looking at this, and how do we think about modeling those mechanisms, and that'll play into these natural mortality relationships that we see here. Is it a kind of baseline, constant, static, additional mortality, or is there some sort of prevalence associated with the environment? And how can we, what's the percentage of mortality that can be, attributed to shell disease across, different sizes of lobster? And then thinking about other biotic interactions, looking at predation mortality. So, lobster historically were predated pretty heavily by fish, and that's no longer, the case here. I think, as Malia was stating in her lobster class, the biggest kind of predator on lobsters are bigger lobsters, which is kind of a new kind of interaction. And how will that change in the future? We know that, species are expanding their ranges, and if there are new predators in the area, what size classes of lobster are most vulnerable? How does that change? So building that into these mortality mechanisms, I think will be really important for the population dynamics as a whole. And then here's where we bridge that gap between the environment and the human dimensions. And so really this is going to become a feedback mechanism, thank you, where population dynamics and the outcomes will feed into fishery behavior. And this will be an interesting framework here to support, like, how do fishers change their behavior based on the population productivity and where they are, and what are the implications, socially and culturally. So some next steps here, all these teams are kind of moving forward in parallel, and so we're thinking, down the road, integrating all of the projects together. And so right now I kind of have a sort of prototype population model that is, functioning, but the ambitious hope is to have a couple different regional population models, each with their own biological mechanisms, each with their own temperature regimes, and each with their own, abiotic and biotic interactions. And so we'll be doing a lot of scenario testing and sensitivities, because ultimately, the goal here would be to identify what mechanisms lead to the most uncertainty in the outcomes. And then identifying those, we can really kind of enhance future understanding of those areas. And so with that, I'll sort of wrap up and take any questions if there's time. Thank you very much.
We have plenty of time for questions. I guess I'll ask a question. On the first few slides, you had plots with red and blue lines. Could you just clarify? I couldn't see from my point of view what those represented.
Yeah. So like these types of things?
Yeah, so what is the red and what is the blue?
Yeah, so this is just kind of like an indicator of cooler temperatures in blue would kind of lead to the blue kind of outcomes, whereas warmer temperatures in red will kind of lead to alternative outcomes. So we think of like more accelerated growth, earlier, less years to harvest size, and a smaller size at maturity.
Thank you.
Yeah.
Thank you. Great talk. And I'm excited to learn more about this project. Thank you. I'm curious if you're going to be exploring any wildly different growth options like they've seen with rock lobster, where growth has actually slowed but maturity has sped up in response to intense exploitation. So I was just wondering if that's something you might, because well, you'll have to come to my talk. I'd be curious to see if that might be some at play here as well in our region.
Well, so they're growing slower but maturing smaller.
Right, because there's like, in effect, the effect of intense fishing pressures. It doesn't make any sense to grow fast because you're just going to end up harvesting.
Yeah.
But you need to mature at a smaller size to be effective and maintain the kind of recruitment and high population sizes we've been seeing. So that's an alternative that lobster folks tend not to think about, that might actually be going on in other regions as well with other species. Something I'm just kind of seeding as an idea among American lobster folks, and I'd be curious to see a run of your model with something like that too.
Yeah, I think that's super interesting. And whether it's a bottom-up temperature effect or a top-down fishing effect, both leading to smaller size and maturity, I think and the interaction between those two is, thank you.
Anyone else? Anyone online?
No questions online. No other questions. Thank you, Miguel.
All right, thank you.
Miguel.